Okay. So let's begin. I recall the formula. So I recall that this is simply the definition. This is simply the definition of the coefficients. The coefficients. These are transition coefficients between two bases. One is formed by the Schur functions, and another is formed by the power sum symmetric functions. And but what is the point? The point is that these coefficients are in fact they are in fact the character table. The character table of the symmetry group. So I assume here that the size of all partitions is fixed and equal to some n. And that is already a result, and a beautiful result, which is due to Frobenius. And maybe his greatest result, maybe even. So I don't want to prove it, because it is some fact of the representation theory, but I would like to comment a little bit about it. There is a way to connect it to the representation theory of the general linear groups. And in fact, if we know the characters of general linear groups, then we can prove this. We can prove this formula. And provided we also know the Schur-Weil duality. Schur-Weil duality. So the Schur-Weil duality plus the knowledge of characters of GLN implies the Frobenius theorem. So the fact that these are exactly the characters of a symmetry group can be deduced from these two facts, the Schur-Weil duality and the knowledge of the fact that the irreducible characters of these groups are given by the Schur polynomials in n variables. So I would like just to to recall you, because I hope that we already know the Schur-Weil duality, but anyway, so what is the Schur-Weil duality? So the Schur-Weil duality.
Sorry.
Yeah?
Can you say again which is your statement of Frobenius theory?
The Frobenius theorem says that the transition coefficients are the characters of the irreducible characters of a symmetric group, meaning that this coefficient is exactly the value of an irreducible character, which is indexed by lambda on the conjugacy class in the symmetric group, which is indexed by the partition rho.
Okay, thank you.
So this formula is simply formal. This is essentially a definition of the coefficients, but the significance of these coefficients is given by the Frobenius theorem. And I would like to give some comment about the Frobenius theorem by relating it to the Schur-Weil duality. Okay? So now I will explain or recall what is the Schur-Weil duality. Schur-Weil duality. So take the complex space, the coordinate complex space of dimension n, and take its tensor power of degree small n. And on this space, on this space, two groups operate. There is a natural action of GLN, because the group GLN operates on this space by the tautological representation. And next, there is a natural action of a symmetric group, just permutation by permutation of the tensor factors. These two actions commute to each other. But this is, I think, evident because they are defined independently, and the picture has the obvious symmetry. So the action of the GLN inside this space has no relation to the action of this group by permutation. So the commutation, the fact that they commute, is obvious. What next? I need a definition of commutant. So assume we have a vector space, and the script A is some algebra of operators on this vector space. Then we assign to it its commutant. It is often denoted as A prime, the commutant. It consists, is the set of all operators in our space, such that AB equals BA for any operator from our algebra A script. Some people say not commutant by centralizer. So one can say equally well that the commutant is the centralizer of this algebra in the algebra of all operators. So this is an equivalent terminology, but I prefer to say the commutant because in operator algebra, people say commutant. And the sure-while duality now is the following claim. Claim of sure-while duality is that each of the two groups, GLN and SN, generates the commutant of the other group. So given a group, its action by operators, we simply have some family of operators, which is closed under multiplication. And we take the linear span, then we get some algebra of operators, and we ask about its commutant. And it turns out the commutant is generated in the same sense by the other group. So this is a fact which is a deep fact and used in many works. It's not difficult to prove, but it's not trivial nevertheless. I don't want to prove it now. I would like now just to deduce some corollary. This is some general argument from representation theory, which says that once we have two groups which are in such a kind of duality, then the decomposition of the space as a bimodule over these two groups looks as follows. We can write this space, so I'm sorry, I will write space as a bimodule. I will use the terms module or representation as equivalent terms. It's equivalent simply means that it can be written as two direct sum of tensor products of certain irreducible representation. So we have here representation GLN, which is a polynomial representation, which means that it is indexed by a partition of length at most n. So here we have, lambda is a partition which is of a length at most capital N, but it also have small n boxes. And here we have this guy. Sorry, maybe it's better to. Okay, so we assume here. I assume that we already know what is this. What is this? Some irreducible polynomial representation of this group, and this is a certain representation for which we only know that it is some irreducible representation which is attached in a certain way to the same index, and representations, these irreducible representations attached to distinct indices lambda are pairwise inequivalent. This is a consequence of a sure-while duality. And next, one can write the same equality, it's the same decomposition as an equality of characters. This can be written as equality of characters. So here I assume that we already know. So assume already know. We already know that the character of GLN with index lambda is the following object, is the Schur function, is the Schur polynomial in n variables. And here these are the eigenvalues. Eigenvalues of a matrix from GLN. So assume that we already know, then one can write the following identity, which is a consequence of this decomposition. Can be written as follows. So take a pair of elements. How to write it? Maybe sigma is an element in maybe okay, sigma and permutation, and G is an element of GLN. We can assume that it is a diagonal matrix. And we want to compute the trace of the operator. I will denote it by T of sigma and J and G. So what does this mean? We have an action of two groups which compute. That is, we have the action, a representation of a direct product of a symmetric group and the general linear group. So this object is well defined. This is a certain operator on the tensor space. But on the other hand, by the Schur-Weyl duality, it is the same as the product of a character these are bad notation. So I assume that rho is the cycle type of sigma, which means that our permutation has a cycle of length ρ1 and a cycle of length ρ2 and so on. This just means that the cyclic structure of sigma is given by rho. And here we write the character of G, which we know is, I assume that we know that it is the Schur polynomial. And it remains to prove, it remains to check. So look at this formula. Look at this formula. It is almost we want. It remains only to check. It remains to check. Check that the trace of element is just the power sum. This is not difficult. Just look at the definition. What does this element, it acts on each copy, and next we have a commuting action of permutations. So this is a certain operator. It's easy to write it explicitly, what is its action of a diagonal matrix times a permutation with a known cyclic structure. And from this, one can deduce that the trace of this matrix, and I would like to emphasize that this action is well compatible with the natural basis in the tensor space. So from this, one can deduce that the trace is exactly this object. So we get this formula, only in the truncated form with polynomials instead of symmetric functions, but taking the capital N large enough, we get the formula in this form with the point that these are irreducible characters. So this explains why these coefficients are of great importance. So you want to know as much as possible about these coefficients, which is not easy because I already said there is no closed formula. We know what we know. We know the key fact about these coefficients, the Murnaghan-Nakayama rule, which is an algorithm, very useful, but only algorithm and not a closed formula. What next? The next quantity, which is attached to characters, is the dimension. So dimension of a character. So this is the dimension of a space, dimension of the corresponding space on which our representation is realized. So the dimension, what is the dimension? The dimension, it is equal to the value of a character. It's the same that the value of our character at the identity element. But in our situation, the identity in the symmetric group, in our situation, its cyclic structure is 1, 1, 1 n times. So this is our row, which is in our case is this partition. So we can conclude from this that the dimension of this character is equal to a particular coefficient. So, and because of this, we are interested in the possibility to find at least a formula for this quantity. How to do this? And for this particular quantity, there is a closed formula. This is Frobenius, again Frobenius formula. Frobenius formula for dim lambda. And dim lambda, it is my notation for this quantity. So this is the definition, this notation, and I want to find some formula. And now I can state the result. Or maybe I would like to okay, I will state the result. result. This is Frobenius theorem. It says the following. So let lambda be a Young diagram, and let capital N be greater or equal to the length of lambda. So this just means that lambda n plus 1, lambda n plus 2 are equal to 0. Then the following formula holds. Take the dimension. It is convenient for me to divide it by n factorial. Then we have the following. Here we have a product of such type. And divided by this product. So what is interesting here? Here there are in fact two claims. One claim is that this formula, so there are two claims. Essentially, the first claim is the right-hand side does not depend on n, provided it is at least equal to the length. This is important. So the right-hand side is stable. As n grows, it does not change. So this is one. And of course, the second claim that the right-hand side gives us the dimension up to this factor. Okay? Both claims are important. So the first claim is easy. It's easy to see. So proof. How to prove the first claim? Just look what happens. What happens? So let's denote the right-hand side. Let the right-hand side. That is, let's denote. Let's take some notation. Okay, so denote it as follows. So we want to show that f lambda is stable as n. So what happens? Look at this formula. And what happens if so what happens? As n we get 1, we pass to the next value of capital N. Then we have that lambda n plus 1 is equal to 0. Okay. So what we get? In the numerator, so what appears? What happens? There are some changes in the numerator, some modification of a numerator, and some modification of a denominator as n grows. And there are some extra factors which cancel out. Indeed, what we have as n, capital N, is replaced by n plus 1. So in the denominator, what we have the product is transformed to this one. But what is this? So this is the same. This is the same. The same times the product this one, and nothing else, because the last coordinates is equal to 0, and the index I for n plus 1 is 0. So we get 0 factorial, which is equal to 1, so nothing more. So this transition amounts to multiplication by this factor. And it remains to prove that the same happens here. So it's an easy exercise to see that the same happens. Because why? Because we have to control what happens if j is equal to n plus 1, but then it is equal to 0, and j is equal to n plus 1, and we get exactly the same product which appears, the same extra product which appears in the denominator. So we prove the stability. So this is for the first claim, the stability. And the second claim, the main claim, is of course not so trivial because it's not pure combinatorics. We need to use the definition of this quantity. It's not just, it's not a fact about some rational expression. We have to use something about this, what we need to have. So I proceed to the proof of second claim. And I need some notation. I need the notation, the definition. It's simply a notation. So I write mu with a row. The means.
Sorry.
Yes.
In the proof of part 1, so I think it's the same times the product from I equals 1 to n plus 1, maybe.
Sorry, I don't understand. Excuse me.
The same times the product from next page.
Mm-hmm. Okay, so this page. What is the page?
Yeah. When you change from n to n plus 1, so you wrote it's equal to the same times the product I equals 1 to n. I think maybe it should be I from 1 to n plus 1, since we have lambda subscript n plus 1 up here.
I don't understand, sorry.
Он спрашивает, почему произведение не до n плюс 1, а до n-того. Ну, потому что там лямбда n плюс 1 будет 0, а n плюс 1 сократится с i. Вот, что он спрашивает.
Okay, so the factors here, I already tried to explain this. The last factor here, which corresponds to the index I equal to n plus 1, is equal to 1. Why? Because this, okay, so I was like, maybe...
Okay, I understand. Thank you.
Okay. So I continue. So this just means that by definition, lambda is obtained from mu by adding a box. So this simply means that mu is contained in lambda, and the number of boxes in lambda is equal to the number of boxes in mu plus 1. Okay. So this is the definition. And now the claim that I need is a recurrence relations. Recurrence relation for a dimension. It says the following, that dim lambda is equal to the sum of dimensions of mu, and the sum is over all mu which are below lambda in this sense. So the sum of here is the sum is over all mu which can be obtained from lambda by removing a single box. Okay. So this is a recurrence relation which allows us to define the dimension inductively. So it means that dim lambda is equal to the sum maybe it's a bad notation, it's just the number of sequences, the number of these sequences, and equally well, which it is the number of standard Young tableau. Before we dealt with semi-standard Young tableau, which means that we have weak increasing along the row and strict increasing down the columns. But standard means that we have strict in both directions. Number of standard tableau with entries in so this is just a reformulation of this recurrence relation, which means that we have, if you want to build a Young tableau, but we have one box, this is one, add another box, number 2, 3 or 4, and so on. And the fact that at each step, by adding a box, we get a Young diagram, just means that our procedure is a filling of the shape lambda by numbers from 1 to n, satisfying these conditions, strict increasing in both directions. and the entries should be exactly 1, 2, and so on till small n. So now we will use exactly this recurrence relation, and what we want. We want to show by induction that this quantity is compatible with the recurrence relation. So we want to prove. So to prove, we want to prove now. Want to prove. I recall my notation, where it is. Oh, it's my notation for the right-hand side. So if we multiply this by n factorials and small factorials, we get the dimension. So I want to prove. I want to prove now that we have the following fact. In factorial, n lambda is equal to the sum of so this is what we want to prove. This is what to prove. Let's let's transform a little bit. Transform a little bit. First of all, we can write this as follows. Is equal to n mu so let's change a little bit the notation. So right. So what we have here is equal to the left-hand side is equal to product it's easy to see that it is exactly the same that appears in our formula. It is the same. It is the, and this is the product of these factorials. So we have the product is factorial. And we want to prove, that it is equal to the sum. Here we have the n. Maybe it's better to put it on the left hand, sorry. Put it on the left. And here we have a similar expression. And we can form similar quantities, which are and what means what means that mu satisfy this property. This just means that this vector is equal to this one minus some vector of such a type. So the next observation, it is very a simple step, but it is important because it used in a number of arguments about symmetric functions. Namely, here we need to have Young diagrams. Okay? So this entry can't be absolutely arbitrary. It should be so that after removing one from a coordinate, we get a Young diagram. Okay, so for instance, if you have some Young diagram, such type, for instance, it's forbidden to remove this box. Okay, so this just means what this just means. This means in terms of the L coordinates, we have strict inequalities. So we can't say take this if a difference is only one, because after this we get two equal coordinates. But if this happens because of this van der Monte factors, the corresponding quantity on the right vanishes. So we can take arbitrary ones. Okay. So what I said can be written as follows. Now our identity can be written as follows. So I don't need this. Can be written as some over say K. And what I want now, I want to divide the right-hand side by the left-hand side. So I will write the result as follows. I will write it as follows. Write the result. So what is written? So I wrote the desired equality. I divided the right-hand side by the left-hand side. Okay. Wrote this in these terms. Okay. So what we get this this identity. I hope it's correct. So the sum and the summand have the form the product of n minus 1 factors, because we exclude R ranges over all indices from 1 to n except k. So this is the difference between the Vandermonde and the Vandermonde, the similar Vandermonde, when exactly one of the coordinates is modified in this way. Okay, so we get this. But what is this? This is simply an identity written in terms of rational function, a rational function identity. Now we can completely forget about the origin of these numbers. We can forget about the fact that they are strictly decreasing, and we may treat them as formal variables. So we have some rational function in variables L1 and Ln, and we have some more or less complicated identity. We have to prove it. How to prove such facts? How to prove such fact? The idea, it's very useful idea. This is why I would like to tell you in all details this argument. The idea is to use residues, just to count residues. So we want to write, we want to find some rational function, some function which is, z is some additional formal complex variable, and for a rational function, we know that the sum of all residues in the extended complex plane on the Riemann sphere is equal to 0. So we want to write this fact. So what is this? This is the following. This is for following expression. So I claim that the left-hand side is the sum of the residues okay. No, sorry, it's incorrect. Maybe it's better to say, sorry. In my notation, it's better to change the notation. So look at this. And compare this and this. Okay. What are the poles? The poles here are these numbers. And no, it's bad. Here maybe indeed we... Okay, but nevertheless, I'm sorry about the notation, but the claim is that the left-hand side is equal to the sum of the residues in the complex plane of these rational functions, but then it is equal to the minus residue of this function at infinity. And now this residue at infinity, just taking the change of variable, as usual in complex analysis, and look at the pole and the residue, and we get the result. And we get the result. So this is the idea of the proof. The idea of the proof. In MacDonald, we can read another proof, but I like this one. I like this proof. Usually, it's not mentioned in the textbooks, but I think it is given in the book. Some reference for this proof is there is a treatise by Donald Knuth, The Art of Computing, and in one of the art computing or something like this. Computing on volume. There is exposition of the combinatorics of the characters and Young diagrams and so on. And Knuth gives this proof. I like it very much. Okay. Now, there are other formulas for the dimension. And probably maybe even more famous than the Frobenius formula. It is called the Hooke formula. Hooke formula. What it says? We need a definition. Definition, if you have a Young diagram, the box. I recall the definition, I already gave it. So we take the hook, so a shape like this, and the hook length, the hook length of a box in the Young diagram is the number of boxes in this hook shape. Just want to compute the number of these boxes. And it is usually denoted by H. And a beautiful formula, the Hooke formula says, the same quantity, the dimension, divided by n factorial is equal to the product of all boxes of the Hooke length. Usually it is written in the equivalent form, the dimension is equal to n factorial, but with product. It's a highly non-trivial result, non-evident result at all. First of all, why? One can ask why n factorials is divisible by this quantity. It's not at all evident. This is some deep result. But how to prove it? My way to prove it, I never saw it in textbooks, but there are various ways to prove it. But my way that I would like to show you, proof, deduce from Frobenius formula by induction. But what is the induction? So what we want to prove? Maybe I need some notation. So some notation. So I recall that we have d lambda divided by n factorial. I denote it as follows. With the remark that the right-hand side is stable. It does not depend on the capital N. And then I want to denote this product. So what I want to prove? So I want to prove that this claim. How to do this? By induction. But now I will substantially use the fact of stability. Up to this moment, the capital N could be arbitrary, but now I have this possibility, take N equal to L, which is exactly the length of so this diagram. So this is length. We have something else. And let's lambda tilde be obtained from lambda by removing the first column. And I want to examine what happens. So I want to compare what happens. So compare, so look at f L of lambda and on the right hand side and compare with tilde and I want to prove that the changes when we pass from, when we remove the first column, the changes on the left and on the right are the same, are exactly the same. So what happens on the right? Look, on the right, we have remove the hooks which corresponds to these boxes. And this is exactly, so we have to multiply by the Hooke length in order to kill these extra factors. But on the left-hand side, we see what we have on the left. On the left, we have this I'm sorry, this is L has different meaning, but I hope this causes no problems. Okay. So we just show that there are the same change on the left. So this is, I think, an easy exercise just to see that the effect of a passage of removing this column is the same on the left, on the right. And so by induction, we can deduce the Hooke formula from the Frobenius formula. So this is a nice argument. But now look, these two formulas are of different type. The Hooke formula is symmetric. It's symmetric with respect to transposition of a Young diagram. We have an evident equality that the dimension of lambda is equal to the dimension of lambda transposed. Why? This can be explained in different ways. One way is to use the recurrence relation and the fact, the equivalent fact that the dimension is the number of standard tableau. And it is evident that the number of standard tableau does not change after transposition. Another way is just to look at the formula, at the initial definition, which says that so write this as follows. Take rho equal to 1, 1, 1. This means and just apply our involution omega. And applying it, we see that the result does not change. That is, the left-hand side does not change, and on the right-hand side, we get lambda transposed. Okay. And the Hooke formula has this symmetry, but the Frobenius formula does not, because it prefers the row length and the columns length, but it can be repaired. There is one more version in lambda in terms of Frobenius coordinates. Recall the Frobenius coordinate notation. We write And this is as follows. So we see the Young diagram, something like this. And they, okay, I will draw the picture. The Darphy square. And next some possible shape which is appended on the right as some possible shape which is appended below. And then the A coordinates are these lengths on the right of the diagonal boxes, and the B coordinates are the truncated column lengths below the diagonal boxes. So these are the A and the B coordinates. And this notation is also symmetric with respect to transposition, which amounts simply to switching the roles of A and B. And the following beautiful formula holds. Is equal to the following expression. So let D is the number of diagonal boxes, a number of Frobenius coordinates. So we have a following expression. Divided by the sum of double sum times the product of the factorials. You see that this formula is, in a sense, more economic than the Frobenius formula, especially in the case if the Darphy square is small and the coordinates, the Frobenius coordinates, are large. In the Frobenius formula, we have to take a huge expression because the length can be large, but here we have to deal with D, which in principle can be small. But anyway, this is another formula, which I think is also nice. And it is evidently symmetric with respect to switching between the A and B. And how to prove it? I propose the following way. The following way is, again, to argue by induction, but as follows. Just look at this picture and compare this result with the Hooke formula, and let's separate the boxes in the Hooke formula. First, we have the boxes inside the Darphy squares, okay, and their Hooke lengths gives us this product, because we have this, you see, the product of ij from 1 to d, this just corresponds to taking the product of these boxes. Okay, so this explains this expression. And now we take this expression, okay, and this expression. And to handle it, we just use the equality between the Frobenius formula and the Hooke formula. as applied to this shape and this shape. Because these A coordinates just are the raw coordinates for this shape. Because the A coordinates are just the raw length plus some additional terms, and these additional forms are exactly this one. And also we use here the fact that the dimension is invariant under transposition, so we can apply, we can freely apply the Frobenius formula for the transposed of this shape, which you read. So to conclude, what I tried to tell you, the Schur-Weyl duality and the fact that the Frobenius formula for the characters, is a kind of materialization of the Schur-Weyl duality, because if you write the Schur-Weyl duality as an equality of characters, we compute the characters on the left, on the right, a materialization of this the Schur-Weyl duality just gives us the Frobenius formula for the characters. And then I deduced from it three different expressions for the dimension. One is the Frobenius formula, this one, Frobenius formula. Next, the Hooke formula in terms of Hooke length, and finally, this similar expression in terms of the Frobenius coordinates. Okay, so that's all for today. So I would like to switch off